Okay, so the idea now is to try to go throughout the Elgamal encryption protocol, let's call it. So let's try Elgamal encryption. And the idea is that if you think about Alice, Bob, and Oscar, where Alice is the receiver of the message, Bob is the sending of the message, and Oscar is the attacker, it tries to break the ciphertext and reveal the text that was encrypted. The idea is this. This is the idea is that we have some kind of a public key and we have a message. We are Bob, which is the sender. He won't be able to decrypt the message, but he sends the message. I mean, think about it of, I don't know, something that you are browsing the web and you send a message to the server. Now the server is Alice. You can send the message. It goes encryption. You can't decrypt it. You, Bob, you send the message. Alice, which is the server, has the private key and it can decrypt the message. But you, after you encrypt it, you cannot decrypt. Oscar can see the public key also, as you can see, as everyone can see. But Oscar doesn't have the private key, so he can't decrypt it because it's very hard to calculate the logarithmic uh, discrete logarithms, and we will see this. So this is the idea of the encryption. It's a public key. It's a public key. Let, asymmetric encryption, if you want to think about it this way. Asymmetric cryptography. So, okay, let's start with the protocol. So you can see here from GPT, it can hallucinate. So I try to make sure that everything we say is correct, but he summarized it quite nicely. So we start with prime number. The first thing we do is generating key. So we start with prime number, and this number is called P, and you need to choose a large prime number. And then we select generator. Remember the generator in secret group is a number in the group. Let's call it G in ZP. This is a number in the group. For using it, we can generate all the numbers in the group. Uh, if you don't remember what it is, it's a number that we can use to generate every other number included itself in the group. And if it's still not very clear, there is a video on it. I did one, but of course, if you find something else, it's probably better. So the next thing we do, we generate the private key. So generate the private key, which is very simple. Generate the private key. See how simple it is. Let's call it X, and it's just a number between 1 and P, uh, which is our prime number, one number from this range. And now we are compute the public key. Everyone will be able to see this private key, and let's call it Y. And the formula for it is G to the power of X in modulo P. It's just G, the generator, to the power of our private key and modulo our P. And this is the and this is the public key. So the, the public key is, let's say more precisely, is the triplet, which is this one, P, G, and this Y that we just calculated. So this is the public key. So let's bold it. This is the public key that everyone will be able to see. Okay, now we generated the public key. Now we can encrypt the message. As so we are in encryption. So in encryption, we are starting with, as you can see, converting the message. If I have a message, we will see an example with hello, so I can convert. You will see that I will convert the text just to numbers. For example, H, it's A, B, C, D, E, F, G, H. So 8. So I can do this conversion, and E is A, B, C, D, E, F, G, H, I, J, A, B, C, D, E. It's 5. And etc. etc. We can calculate, I'm not sure, let's see the example here. We have an example here. As you can see, this is what I wanted to show you. This is the conversion. Okay, now let's just choose random number, which we call k. Now we will have for each letter another k. So k1, k2, k3, and etc. etc. Here we have 1, 2, 3, 4, 5. So until k5 in this case. Now compute the ciphertext. We will compute two things, the C1 and C2. C1 and those we will for each letter you will see that there is ciphertext. For each letter there will be C1 and C2. So C1 will be G, it's our generator from here, to the power of K. Now for each letter there is different K, so for each letter there will be different C1, mode P, and C2 will be this M that we got. So for example for H it's 8, so let's call it just M. For each letter there is different M, times Y, don't forget this is the Y to the power of the certain K we have. Maybe let's call it Ki, because I want you to remember that it is for each letter separately, and this is mode B. Now for each letter I will have this pair C1 and C2. So for each letter there is C1 and C2. If you look at the example that we will see later, you will see that in the end what we get is for each letter you will have a pair C1 and C2. For H, C1 and C2. For E, C1 and C2. For L, and etc. etc. So in a minute we will see an example, but let's finish the idea. So we encrypted, we generated the key, we generated the public key. This is it. It's very important, so let's bold it up. We generated the public key, we encrypted the message. For each letter and letter we created this ciphertext pair for each letter, which is C1 and C2. Okay, so we encrypted the message, and now we are in the stage of decryption, decrypting the message. So we start with compute the shared secret. We're starting with shared secret, let's call it, which is S, which is C1. For each letter we will have C1 to the power of P, and again everything is mode P, and it's like, now see that this is C1 to the power of X, so C1 is just this one. So if you take it to the power of X, you'll just add x to the power of the g, so this is why they're telling you that this is like this one. So we can say that this equals, if you open up the C1, you get g to the power of k. In our example, I wanted to tell you that it's ki, to remember that this is for each letter. Ki times x, which is the secret key. So the one that does the decryption should have x, which is Alice, and Alice alone, the receiver, and no one else. So only Alice has this x. So again, this is all modulo p. So this is the shared secret. Now inverse, find the inverse of the shared secret. So we want to find s to the power of -1 such that, as inverse should do, it will give us 1 in modulo p. So we need to calculate this inverse. And now we can decrypt the message. So the current letter, let's call it mi, decrypt. So mi will be equals to C2, remember the C2 from here? C2 to the power of S multiplied by S to the power of -1, which we got from calculating the inverse. Everything modulo P. This will give me the value for the text. For example, for H, I will get again the value 8. Okay? So I think it's time to look at a full example, which is what you see right over here. So let's walk through an example. But again, look at the protocol. Let's again, key generation, the public key generation, prime number generator, and private key X. We are creating the public key, and X stays with Alice, let's call it, the receiver. We encrypt the message. For each letter, we convert it to a number in any method you want, just know what is the method. We convert it to a number, and for each letter, we create from the plain text, which is hello, for example. It's an example here. Example, yes, you may have different messages, different examples. For each letter, we create C1 and C2, which is the ciphertext. So for each letter, I will have C1 and C2. This is the encryption. I convert the plain text to a ciphertext. And then I do decryption. Alice, the receiver, can do decryption because Alice has the secret key, which is X. And how? It calculates the shared secret, C1, which is part of the ciphertext of the current letter, to the power of x, which is like g to the power of c1 is this one. So it's c to the power of ki x modular p. After we calculate s, we want to calculate the inverse. The inverse, again, it's s times s inverse equals 1 in modular p. And then after we have s to the power of -1, we can decrypt using C2. We are just multiplying the C2 of the ciphertext of the current letter by this s to the power of -1 in modular p, and we are getting the current letter. Doing it for each letter, we will get the value for the plain text. And we can convert this value as we did. For example, h equals 8, so we'll get 8, and now we can convert it to h, for example, for the first letter h, and for each letter the same. So this is the protocol. Now let's see the full example of how it works. We'll see the values. So again, we are doing the protocol, just giving an example. So we calculate and we choose a prime number which should be big, but here for simplicity, we will choose p equals 17 because it's simple and easy. We are choosing a generator. Let's take 3 in Z17 without zero, so it's Z like this. Okay, this is a generator in the Z17. Choose a private key. Again, we are choosing private key, as you remember here. This is this one. Private key from this range. And we have P17, so we can choose a number between 1 and 15. Let's choose here 15 because this is what it shows. Okay, and we want to create the public key, so we are left with calculating y, which is t to the power of x modulo p. So it's 3, which is g, to the power of x, which is 15, in modulo 17, and you can see here the calculation, and it got, maybe it's wrong in the calculation, but the idea should be, the idea is the thing that I want to teach here, and we got 7 for y. So now we can create the public key, which is p, g, and y, which in our case is p, which is 17, g, with it, which is the generator 3 of the group based on the prime number we chose, and the y that we just calculated, which is 7. This is the public key. This is very important. And maybe I should have said, and this is the private key, which is x. Okay? So this is the, let's call it the key generation step, or the keys, because we are creating here the private and the public key. Okay? Now let's go to encryption of a message. Let's encrypt again the example that I wanted to show you. Let's encrypt the word hello. So H is 8, E is 5, L is, what did I say, 12, and O is 15. Okay, so we have, it's not the ciphertext, in the plain text, just numerically. Ciphertext, remember, we want to create it. This is just a numerical representation of our plain text. Okay, this is what I called M for each value. Now we want to choose a random number, so we get a k, which equal, let's choose 10, and again remember it's between 1 and p minus 2. Now let's compute the ciphertext for each letter, and remember the ciphertext is C1 and C2. So for each letter calculate C1 and C2. That's what we are going to do now. So C1 equals, for the first letter, let's do it like H, okay? So C1 for the first letter, again, this is J to the power of Ki. Okay, okay, this is for the first letter. Everything is for the first letter because K is also for the first letter. So let's call it Ci1, J to the power of Ki, again modulo P, and this is, the generator is 3, the K that we just chose is 10, and the modulo is our P, which is, we know it from the public key, here it is, which is 17. Okay, now what we are going to do is compute the Ci2, let's call it, because it's of the first letter. And again, we are computing it using mi times y to the power of ki and everything modulo p. And again, it's for 8, so 8 equals 8, h equals 8, so mi equals 8. What we have as y equals, we know what is y because it's here, y equals 7, ki equals 10, and this is all what we need to calculate. M we have, y we have, k we have, so we can calculate C2, which gives us, okay, we need to calculate this very big number, 7, or y to the power of ki, which is 7 to the power of 10, and everything in modulo p, which is 17. And you can see here the calculation, and if there is no mistake and hallucination, so we get 11. We get 11. Now we can calculate the C2 again for this letter. So I need to say CI2. This is for the H in this case. So Mi is, as we said, 8 for the letter H, times y to the power of k modulo 7 that we just calculated, which is 3, or wait, this is, yes, this is 11. So this is 11, and everything again modulo p, which is modulo 17, because our p is 17, part of the public key, and we get 3. Great, so we got a ciphertext for the first letter. Ciphertext for the first letter, in our case, H, and we got C1, which we calculated and got, oh, I didn't say what is the value. Oops. So the value is 13. So we have C1, C2 for this letter, which is, in this case, it's 13. This is C1, and C2 is 3. Okay, so we have H, the ciphertext, let's call it the plain text, is H, and we got the ciphertext, which is 13.3. So here we encrypted the first letter using the encryption. Elgamal encryption, sorry. Yes. Great, and we are doing it for the other letters, and you can see here it did it again and did it differently and chose another K, but you can see in the end you will get, for each letter, you will get the ciphertext for each letter. Okay? Okay, now what are we going to do? Now we're going in the decryption part. So decryption. After we did this for each letter, again, plain text for the next E and ciphertext, whatever that will be, with its own C1 and C2. Okay, and for everything else, hello. So HELLO, every letter will get its own ciphertext. Now we are in the decryption part, and this is the last part. And only Alice can do that, because only Alice has the private key, which is X, which is a very simple number, but it's very hard to get. Oscar doesn't know X. He does know P, he does know everything in the public key, P, G, Y he knows, but the X he doesn't know. And therefore he can decrypt the message. So how we decrypt? We calculate in S, C1 to the power of X, and we are decrypting for H, which again is 8, which has C1 of 13 and C2 of 3. Okay, for each letter you need to decrypt its value. And remember that X, this is the private key. X, which is the private key, only Alice has it, is the value, which is the value of X that we chose. Here it is, 15. Okay. So we chose X private key to be 15. So we can calculate in modulo p this way. We can calculate it and we will get C1 to the power of 15 and everything modulo 17. We will get, let's say, 11 if there is no hallucination. Now we want to get C to the power of minus 1, which should satisfy C in the group, C to the power of minus 1, and it should equals E1 in modulo 17 in our case. Uh, okay, now let's calculate it. So if we have S equals 11 and we want 11 times something which is the inverse equals 1 in modulo 17, so we need to calculate it, but you will get that as minus 1 equals to 14. So we got S to the power of minus 1. So we have S minus 1. Now we can decrypt the message. Mi will get the value for H is C2 that we have, it's part of the ciphertext, times S to the power of minus 1. Everything is modulo P. So in our case, it's C2, which is 3 in the ciphertext of H, times the inverse, which we just calculated, which is 14, everything modulo 17, and we get 8. And remember, H was 8. So here, we decrypted the first letter, and we can do it for each other letter. And why we could do that? Because we have X. Because we have X. Now, remember, okay, here you can see everything it does. Okay, so this is the Elgamal encryption. The protocol is key generation, the private key and the public key. Public key everyone sees. Private key X remains in the receiver in Alice. We are doing the encryption part. Bob, which uses, I don't know, the web, send a message to the server, for example. The message goes encryption, and the server can decrypt the message because he has the private key. Oscar, which is the attacker, can also see the public key, but Oscar doesn't have the X. It doesn't have the private key, so it cannot do that operation. It cannot do that problem. It cannot solve for S, even though he knows P. And he can, I don't know, he can get, I don't know, the C1, but he can't solve the discrete logarithm problem. Remember, maybe I will show you this. If I tell ChatGPT that discrete logarithmic problem, he will show me, if you will be nice, he will show me the discrete logarithmic problem, which is this one. And solving this problem, discrete logarithmic problem, which is the main power, solving this problem, solving it for x is hard. Given a prime number b and a base g, and a number y, the discrete logarithm is to find the integer x, which is between 0 and p. This is hard. This is a hard problem. And this is, look at this formula, discrete logarithmic problem. We need to find x, we know g and y and p. Now look at the ciphering, look at the decryption, look at this one. Okay, g is usually, where it is? G is a generator, so it's not exactly this one, but okay. Yeah, okay, so the bottom line that Oscar doesn't have the X, so it's a very hard problem to solve what is the decryption. That's it. Thank you very much. This was about the Elgamal encryption scheme. If there are any mistakes or correction, please tell me. That's it. Thanks, ChatGPT. If there are any mistakes or hallucinations, I'm sorry. Correct me. See another video. Whatever. Thank you very much, and that's it.